Hi. Hi, it's Noel Markham here. Thank you very much for including me as part of this conference. It's been a really wonderful day so far. I've really enjoyed all the talks. I think it's been really, really good to see just the quality of these talks and how good they've been, considering, a lot of the people in Discord are saying they haven't been doing Scala for very long. So it's great. It's great. I'm really, really excited to be writing Scala, and with Scala 3 being released today, I think it's a really, really exciting time to be part of this community. Thanks also to the Guardian and to 47 Degrees for setting this up. It's been a really, really good day so far. So if we pull up my slides, yeah. So the title of this talk is "What I Wish I'd Known When Learning Scala," or maybe a more appropriate name for this would be something like "Being Purely Functional in an Impure World." And we'll go over some things. Yeah, it's kind of things that I've learned as I've gone along, and probably things that if I'd known when I was learning and when I was starting out, probably would have made life a little bit easier. So again, just to kind of recap who I am. My name's Noel. I do work for 47 Degrees. There's some contact details for me there. I'm also on Discord all day. So if you have any questions about this or about anything else in Scala or career development in general, please do let me know. So I started out a long time ago now as a Java developer, mainly in finance. It culminated with me writing a book. So if this Scala all gets too much for you and you want a job back in Java, I would recommend this book, but I don't have a discount code like Daniela, so maybe buy her book instead. And I've been doing Scala since 2012. I've worked across many industries by now, done some games that were on Facebook, worked at several startups, some kids games, some chat applications, worked at ITV for a little while, worked in the fashion industry as well, and many more. Okay, so these are the things we're going to talk about today. There's actually quite a lot of overlap with Daniela's talk, which I think is okay. Daniela covered these as well, and I think it's good that we're covering a lot of the same things, because it shows that this is valid. Both Daniela and I have had similar concerns, and also, we can put our own spin on these things. So yeah, I think this will work out okay. Okay, so the first thing we're going to talk about is a couple of big words here: parametric polymorphism. Okay, so what does this function do? Okay, we see this in an API document. It's kind of fair to say we'd have an idea of what this would do. We give it a list of strings, and it reverses the list of strings. Okay, and here's another one. Oh, right. So it doesn't do exactly what we thought it would do. Okay. What about this function? So we might have seen this phrase identity before, and usually that's a function that returns itself. Okay, so we would expect if we give it a value, it returns that value. But then, of course, whoever wrote this forgot to actually fill it in and just left the stub implementation. So, like, what can we do about this? Yeah, like, is there anything we can do to make this better? So what we can do is we can introduce type parameters, which sometimes are called generics. If we revisit our identity function, it looks like this. Okay, so now we have this type parameter A, and we're saying we want to return whatever is given to this function. Okay, so there's not really a lot else we can do here. All we can do is return it. We can't add one. We can't reverse a string. We can't truncate a list because we don't know what the value we're going to receive is. All we know is that whatever we give, we're going to return back. And this is really quite powerful, right? Because how many ways can this be implemented, right? We can return ourselves, and that's it, yeah? And also, there's a bonus here. Although we're looking at the identity function for integers, this is actually working for all types. So we never implemented this for strings. And we look at the previous slide, that was just for integers. But now we can use this with strings, or we can create a case class tomorrow that's never existed in the world before, and that will work with this function. Okay. And we can look at the reverse function we wrote as well. Okay, so now we're going to parameterize this, and we'll say, well, we don't care what list we're given. It's just a list, right? And so an implementation might look something like this. Okay, so if we have an empty list, we return that empty list. If we have a non-empty list, we're going to recursively call it and then append our head onto the end. Okay. And this now works as expected. And what does this give us? Is this guaranteed to work like inverse, like the identity did before? Well, not necessarily, right? You know, we can still do lots of different things with this list, even though we've called it reverse. We could just return nil all the time. We could take the first element in that list and return that instead. But we do have some information that we can infer from this type signature, is that the values that are returned from this type from this function are only ever part of the input. So we can't produce hello world if we give it test input strings. We can't return 0 if we give it a list of 6s. We can't do anything like that. We do know that whatever we get out was somehow part of what we put in. Now, this is not as strong as we saw earlier with our identity function, but this is better, right? We're a little bit more comfortable doing things like this because we know we're going to be able to infer some information about what came from the list in the first place. So it's a little bit counterintuitive, right? That's that we've added a constraint to our functions. You know, we've said we want to specify that it's going to be the type that's returned is the type that's gone in. You know, it's a constraint. You know, we're not saying we can return any string. We're saying we're going to return a specific thing, a specific string, a specific list, things like that. But we've actually set our code free. Right? This is more general. You can see that we have one implementation, but regardless of what type we want to use it with, this is going to work, okay? But we also know nothing about the input, which means we can't manipulate this in any way. We can't return oranges when we get apples. We can't return zeros when we input 6s or strings or things like that. We cannot manipulate this in any way. And the types are our documentation as well. We saw with the type signature for our identity function, we know so much about that now. We know that the value that is returned is the value that's put in because there's literally no other implementation that we can do for that. Okay. So this is a little bit stronger than unit testing. I'm not saying it's better than unit testing, but I mean, there is an argument that could be made there. You know, if there's only one way to implement a particular function, there's probably only very few ways to test it. If we think about how would we go and implement a test for our identity function, well, there's only one way we can do it, right? It's not like, you know, if we were fixing this to integers, we might want to check that every integer was returned as it was. You know, return it with 6, return it with 5, max int, min int, 0, 1, -1. But we don't need to do that because that we have no information about what we're dealing with. So the only thing that we can do is test that what is put in is returned. Okay, we'll move on and we'll talk a little bit about immutability. And how does this differ from other languages? Well, in Java, you have to specify that if you want something to be immutable, it's going to be final. In C#, I'm not a C# user myself, or ever have been, but I believe it's similar to Java. That there's a keyword we have to affix to variables, being read-only. And I think the thing to take away from this here is that immutability is switched off by default. Okay. And then if we look at functional languages, well, Scala has a complete keyword for it. You have to say that something is that way. In F#, again, not really part of the .NET family, but similarly, they have a word ref for mutations. Okay. In Haskell, it's not even possible. Okay, so immutability is switched on by default. So it's quite nice from the imperative world for saying something is final or saying something is immutable. As the author of the code, you're being really quite explicit and saying this code will not change. This value will not change. And then when people read that code later on, they're going to have such confidence with what they're seeing. But I think the opposite also holds here, is that when things are immutable by default, you have to jump through hoops. You have to have a hurdle in order to say something is mutable. Yeah. So what's the point of this? Well, immutable values, they just can't change, right? Obviously. But this means that state can be shared across concurrent running code. We know that it's never going to change, so we don't have to worry about race conditions or things changing when we're not expecting them to. It's immutable. It's never going to change. Okay, but state can also be shared across arbitrary pieces of code, and this might seem a little surprising, or maybe doesn't make sense. But we'll take a bit of a look here. So say we had a couple of lists. Okay, we've got x's and we've got y's, and in memory they might look something like this. So they're Scala lists, so they're linked lists. X's points to the head of the list, which is 0, and 0 points to 1, and 1 points to 2. And similarly for y's, we have the same setup there. Let's say we introduce z's, right, or z's, which says that we want to concatenate x's and y's. Well, if this is new to you, you might think, well, we're just going to create copies of the list, and then we've got a copy of z's as well. But that's actually not what happens. Okay, so x's stays as it was, but z's it prepends the values from x's onto y's, and then y stays as it is as well. So the pointer to y's hasn't changed, but z's has been able to take advantage of the fact that this is immutable and take the end of x's and then point it to y's. So we get to share memory here, and we have the confidence that nothing's going to go wrong with this because these values are never going to change once they're set in memory. Like, you imagine if this was mutable, and someone came along with y's and changed the 3 to a 5, then all of a sudden the values inside z's would change as well. Or alternatively, we wouldn't be able to have a setup like this, and we'd have to use more memory, especially when things we think or we know are probably not going to change very often. And this is not just for lists as well. So here's a slightly more complicated example. We have some kind of binary tree set up, and we want to add another value into that tree. We don't need to create a copy of the tree. We're only going to update all of the parents of the values that matter. So E was inserted where as a child of F, which means that F needs to change, which means its parent needs to change all the way up to the root. But the rest of the tree stays the same. And then for viewers of X's or Y's, they see the tree that matters to them. It doesn't really matter that the memory is shared. It's not even a concern for the developer. Okay. And so if we take a look inside Scala, once we've been working with Scala for a little while, we want to see how things are implemented. And we'll look at, say, the drop function in list. We can see here that, well, actually, this goes against everything I've just said, right? Is that all of a sudden we have vars, we have a while loop. I can't even remember the last time I wrote a while loop. Count has a minus equals. Don't think I've ever written that in Scala. Yeah, this is not really what we signed up for, right? This is mutable. This is maybe makes me highly uncomfortable seeing this. So it's mutable code, right? And it's in the standard library. And why are we doing this? Well, there's a phrase that you may have come across which says that premature optimization is the root of all evil, and this is not a premature optimization. This is a necessary optimization. This could be written in a immutable way. I'm sure that this would be simple enough for most people to write. But what we want to do here is that this code is really, really going to be part of the nuts and bolts of list operations across the whole of the Scala ecosystem. And so performance is really what matters here. And that what you might find is once this has been written in an immutable way and the function contract is defined and the behavior is defined and any tests are written, we can then start to iterate inside this function to create a more performant approach. Everything inside of here stays inside of this function. These variables don't leak. This is all within this function. We know that these is never going to be available outside. So for the people who are using this function, they don't really know or care that mutable code lives inside here. This is still going to work as you'd expect. You're going to retrieve a sublist of whatever the larger list was in the first place. And as you dig around inside the Scala collections, you'll start to see this more and more. And it's okay. Like, these are necessary because this is not always about getting things right. The getting things right part has happened. And now this is about making sure that they are performant. And this is a good thing to think about when it comes to iterating on code, is that it's much easier to make correct code faster than it is to make fast code correct. So often, if possible, start with an immutable approach. And if you find there are performance bottlenecks, then this is a good place to then go and look and see what needs to happen. And it's okay to write mutable code in the right way. It needs to be justified and it needs to be contained. I don't think I would ever be comfortable exposing something that could mutate, at least without lots of caveats and documentation and clear communication with anyone using that code. Okay. So as I said here, it's really, really quite simple to step outside of the boundaries of immutability. Like, we can easily do it, right? We can just put vars in. I did a talk at Scala Exchange a few years ago, and I, for convenience, I wrote a var, and someone got up and left. So it does happen. Okay, but there are things you can do to help with this. You can turn on compiler warnings, and then you can go one step further and make these compiler warnings errors. If you make as many barriers as possible to writing mutable code, at least when you have to do it, you're going to have to be able to justify your decision. Now, it's not a blame game, but if you have to commit some code to say, I've made this mutable, I think that means you're going to give it a bit more consideration and make sure that you're comfortable being able to explain what and why you've done something. Most IDEs are now going to be warning you about writing mutable code. I think even IntelliJ makes vars red, so that they kind of have the appearance of an error, but it kind of scratches away at you while writing your code. And then also there are lots of plugins for continuous integration tools, and also with SBT to alert on code style, which will alert you to mutable uses. And this could either trigger some warnings or some errors within your build that would then need to be addressed. Okay. The next thing I'd like to talk about is referential transparency. Okay. So again, it's another pair of big words, but really all it means is that if we call something with the same input, we are going to result in the same output every time. Okay. So this has some effects that can happen at compile time or at runtime, is that the compiler or the VM can defer execution to a time of its choosing. So if there's a chance that this code may not even be executed, then there's no point even working out what value should be. Similarly, it can replace any function call, the result of that, with any subsequent function calls as well. So if you have some long-running calculation that returns a value and then it's called with the same inputs, you may be able to justify that really the calculation shouldn't have to happen again. If it's referentially transparent, it's the compiler or the VM can just replace whatever that original call was with the value it received before that. Okay, and this is not unique to functional programming at all. And again, some languages, they don't enforce this. This is kind of almost a slightly academic approach. But what it does, what helps is that if you need to start thinking about referential transparency in your day-to-day work, okay, and we need to start thinking about side effects. Side effects or effects are things that affect the outside world in some way, or you are affected by the outside world. For instance, printing to the screen, okay, interacting with the database, writing to a file, asking the operating system what the time is. These are all things where if you run them more than once, you're going to get a different to a file and then you write to it again, it's a different file. It will have a different timestamp in the operating system. It will occupy a different disk space. Okay. If you write something to a database and then depending on the query, make that query again, it's probably going to affect the database in a different way. Even printing to the screen, while it appears that's just something that you fire and forget, it has an effect. You know, if you're writing some kind of game or something that's going to require input fusing, if something is done more than once. Okay. So one thing to do here is to aim for your functions to only do one thing, okay? And one thing only. So if you're going to update a database, don't write to a file at the same time. When you're going to have some affecting code, be clear. Make sure it's clear. Document it well. If you have the opportunity for your programming language, such as Scala, to help you with this, then use it. So for instance, with Scala, you might want to use a future or IO to signify that this is going to have some kind of effect. You know, if you have a function that takes an A and returns a B, there's a level of confidence you can have there that you can call that with as many A's as you want, as many times as you want, and it will not have an effect outside. But if you're calling an A and it's getting an IO of B, then it might not be clear what's happening, but at least you've got a signal here that something is happening, that you need to go and identify what's happening. And it might be clear, you know, if your function is called printline, it's safe to say that that's going to print a line. But if it's IO of unit, you might have to go and work out what this is going to do. But this is a good marker for you, for the future you, and for your colleagues as well, to say, well, actually, we need to be sure that we don't call this multiple times, or if we do, we're doing it in the way that we should. For those that are slightly newer to Scala, the future in Scala is different to Java's future, but I think most people now tend to kind of gravitate more towards the IO in Cat's effect. Okay. Similar to what we've seen already, it's very, very easy to step outside the boundaries of immutability. Even with Scala, you know, we're not forced to say that something is in an IO if we're going to write to the screen. We can just do it. But you know, as more experience we get, we need to really kind of be aware that there's more to our code than just the function, the signature of the function. So we want to establish conventions within our team. We want to lean on the compiler where we can. Okay. And then to kind of wrap a few things up here and move on a little bit, I'd just like to focus on a few things that may not exist, or maybe new to you if you've come from a non-FP background. Okay, so the first thing is type classes. So this is defined with more complicated words again, such as ad hoc polymorphism, right? Which, you know, no idea, right? It's nothing to do with object orientation. It's nothing to do with OO classes. Polymorphism is not implemented in the same way. But a nice way to think about a type class is it's effectively the way to add an interface to a class that's already been defined. One example I often use is that, say, if you come from, say, a Java world, there are some functions that you might find that say they want to compare values in a list. Say you have a list and you want to find the largest value in a list, and then your signature with the Java generics might say that it has to implement the comparator object or the comparable object. Well, if the object you're working with doesn't implement comparator or comparable, there's nothing you can do. It's up to the author of that class to change their implementation. But type classes get around this. This is a way for us to say, I have a type here that I want to be comparable, and here is how I make comparisons with that type. And type classes are a really, really strong part of Scala. And it just means that you can provide like interface style definitions, and then you can provide the functionality for types that already exist. Okay, so if we wanted to write our own toString functionality, often that's called show. We could have a show type class with a function on it that takes any old type A, and returns a string. And then we can then provide instances of show for any type we want, written by someone else or by ourselves or by our future selves, and it will work. We've actually been doing a series on the 47 Degrees blog recently on some Scala 3 information. And there was an article went up last week about type classes, and it introduces type classes in a lot more detail than this one slide will do. So I would recommend having a look at that if type classes are new to you. Okay. Another thing that kind of comes brand new to functional programming is this idea of property-based testing. Okay, and this is a library often called. There's a few libraries, but the main one is called Scala check in the Scala world. Okay, and this allows you to specify properties about your code and let the tests provide the data. For instance, here is a test that we could write using Scala check. Okay, and then what we're saying here is that we're going to somewhere else. This is just a regular test, and we'll say, well, for the reverse function for a string, we want to make sure that this works correctly. And if we look at the way this works in, say, traditional unit testing, we would have some dummy data or some test data and make sure that when we reverse it, that the string is reversed and things like that. But what this does is that we're saying to this library, I want you to give me the string, and I will tell you what I expect to happen to it. So we need to think about things in a slightly different way. So one property of reverse is that if you reverse something twice, you get the same string back. That's not the most comprehensive test ever written. It doesn't mean that if this test works that your reverse function is correct, but it is a property that must hold. So if we reverse something twice, it would hold. We would also expect, if we take the head of a string and reverse it, that character would then be the last element in the string, and things like this. We would expect that the length of the string would never change. Things like that. These are all properties that would go into that. But the nice thing here is that we then don't need to think about test data, and we can let something like Scala check provide the corner cases and the data for us. And a funny aside, I worked on a chat application a few years ago, which was kind of aimed at people younger than me. And so we would test this with Scala check, and it would provide lots of ASCII strings, but it would also then start to provide emojis and kanjis and all the things I would never think about testing. And then lo and behold, when this was then released and put into production, all the cool kids that were using it were using all the emojis, and everything just worked because our property-based testing had done this for us. Okay, and what this does is this doesn't provide just one string. This will run this test 100 times. And what then happens if a test fails, it will try to kind of find the smallest data size it can that causes a test to fail. And we can run into some funny situations with this. For instance, like this seems like a reasonable test. Like the math.abs function comes from the Java standard library, but actually this fails because you may not know, but there are more negative numbers than positive in the Java integer due to the way it's implemented with two's complement arithmetic. But the integer min value has no positive equivalent. So if we negate it, then we get the same value back. And Scala check find this for us. And you can see it tried to run 100 tests and it failed after 8. So it probably ran it with 0 and 1 and -1. And then eventually it started to try more ambitious values and found that the integer min didn't work. Okay, so that's really about all I had to say. We have covered quite a lot here, so just kind of recap this a little bit. We talked about parametric polymorphism, which is adding constraints to our code, which appears to constrain us a little bit. You know, we're locking down what we can do with things, but actually this gives us a bit more freedom in that we don't often have to think about a lot of the implementations we would need to write otherwise. We talked about immutability. So by appearing to be less efficient with our data structures, we were able to provide a lot more functionality and confidence in the code that we wrote. Okay. And referential transparency. We don't want surprises. We want to say, if I call this, I get this value back. If I call it again, I know what I'm going to get. If I'm going to make a side effecting call or an effecting call, I want to be explicit when I do that. Okay. And so I think it's over to you now. Try to use some of the guidelines I've talked about here in the way that you approach things. Try to write functions that are clear to your colleagues or your future self as to what your intention was when you wrote it. I mean, whenever I write code, 6 months later, I come back and, you know, I have no idea what I wrote or why I wrote it. But lean on whatever you can within your language in order to make sure that you can have as much confidence with what you've written. Languages, especially Scala, it can be quite easy or tempting to cut corners, to put a cheeky var in this, make sure that, you know, we'll put a cheeky var in here, and then no one's ever going to call it, and lo and behold, you then other people are calling it, and you have concurrency issues and things like that. But this is all about a mentality. This is all about making sure that we're doing things the right way so that others can follow in our footsteps and see that what we're doing is going to produce more confidence in what we write and why we do it that way. Again, that's all I had time for. My contact details again. You know, I'm more than happy to speak with people if I've said something wrong, probably, or there's some clarification needed, and I'll be in the Discord for the rest of the afternoon as well. So thank you very much.